Right, so let's go over the questions that were on the Nearpod quiz. What values would remove the discontinuity of the given function? Right, so sorry you had to read through A, B, C, D, E, F, G, H, I, and J on that quiz, but did you figure out the right answer? Well, it is, oops. So f of 0 is where we have an issue, and there's no way to fill in the hole. It does not exist. Matter of fact, because there's no hole, right? We have something else going on, right? So we're finding where our discontinuity is and what fills it in, and f of 0 just does not exist. Let's take a look at y. And before I solve it out, I want to just remind you of the steps for rewriting absolute value, right? So we'd gone over this before. In fact, I think you have these very notes, right? So to rewrite absolute value expression in parentheses, we have two parts. We have a -1 and a +1, right? So we take the stuff that's inside the absolute value bars, right? And either it's going to be positive or negative, right? So we plug in something and we get something positive, or we get we could plug something positive in there, or we could plug something negative in there. We get the same value. All right. So we're getting rid of the bars by rewriting it as the two pieces. Right. The one that gets the negative is the less than. Right. If there's anything else with the absolute value, then it gets distributed in, added in after we've rewritten it in parentheses as either positive or negative. Right. So step 1 would have f of x equals 2x plus 3. And negative 2x or minus 4, and negative 2x plus 3 minus 4, right? And then we would distribute the negative and combine the like terms. So that would give us f of x equals 2x plus 3 minus 4, and negative 2x minus 3 minus 4. And of course, we could simplify that to f of x equals 2x minus 1, and f of x equals 2x minus 7. Now we need to know when this occurs, right? So when do we switch from one to the other? Right? So you got to find your breaking point. To find your breaking point, you set the absolute value expression equal to 0 and solve for x. Not anything else with it, just what's in the absolute value bars. So 2x plus 1 or 2x plus 3 equals 0. Subtract 3, divide by 2. Right? Your breaking point is at x equals -3/2, and that's where you switch rules. Right? So that gives us right over here our piecewise function. F of x equals 2x minus 1 if x is greater than or equal to -3/2, and 2x minus 7 if x is less than 3/2. Right? So you need to know where the problem, where it switches, and it's going to switch at that whatever makes what's in the absolute value bars equal to 0. Right? So if we were graphing it, right, it would switch from having a positive slope to a negative slope right at -3/2. All right, so now let's go back to this one here, now that we've done that. All right, so we have f of x equals, we have the absolute value of x in the numerator and then x in the denominator. Let's rewrite the numerator first. All right, so we're going to rewrite the numerator. Right, and as a piecewise function. All right, so we have f of x equals, well, it's not very difficult to rewrite that. We have, right, x, right, for the positive, and then we have negative x, right? There's not much to that, right? So here's our, because that's all we have in absolute value bars, right? So this is our positive, and this is our negative, right? No teeny tiny expression inside this absolute value bars. All right, need to know the breaking point. Well, you just set what's in the absolute value bars equal to 0. And, well, that's x, right? So 0 is our breaking point. Right? So for the numerator, as a piecewise function, And actually, yeah, I guess I want to call it f of x. Let's just call it y for now. So y equals x if x is greater than or equal to 0, and negative x if x is less than 0. Right? But we're not done yet, because this was not just an absolute value expression, right? This was a rational function. So now we're going to rewrite the function using that piecewise function in the numerator. Right, so that's going to give us f of x equals, right, so we're going to have x divided by x if x is greater than or equal to 0, and then negative x divided by x if x is less than 0. All right, so there's it as a piecewise function, as a rational function, but now let's think about that. All right, so, well, what if we reduced? So f of x equals 1 if x is greater than or equal to 0, and negative 1 if x is less than or 0. All right, so we literally have, where can I put it? I'll put it here. We literally have this. Our piecewise function looks like this. So here's that side of the graph, right? There's the positive side of the graph, the x greater than or equal to 0. And then on the other side, on the negative side, we have this, right? So what kind of discontinuity do we have? We have a jump discontinuity. All right, you can't do anything to fix a jump discontinuity and make it make that continuous. You can't make a jump discontinuity continuous. That is always discontinuous. Right? That is non-removable. So that's why it does not exist. Let's look at this one. What values would remove the discontinuity of the given function? Right, so I needed to figure out which is the value, and I also have here where it occurs. And so if you said f of negative 3 equals negative 3, so if you said A, you were correct. Right? That value would remove the discontinuity. Let's look at y on the next page. Right, so let's factor this to rewrite this. Right, so we have f of x equals, now of course we just factor out the x times x plus 3 divided by x plus 3. Oh, look at that. All right, so we have a whole where x plus 3 equals 0. And if we subtract, that's x equals negative 3. Remember, a whole is a removable discontinuity. Right, so that is removable. So now we just need to rewrite this as a piecewise function. All right, so we need to substitute into the reduced function. Okay, so here we reduced to find the whole. Find the whole. Right, and then we're going to substitute into the reduced function. Right, so our reduced function is just x. Right, so if we plug in negative 3, we just have, actually I'll just make it as a function. I'll keep the f. So if we plug in I'm sorry. First I want to write f of x equals x, and so f of negative 3 equals negative 3, and there you go. So the rewritten function, we just had to find what the value was, but if we were to rewrite this, now I'm going to just switch it to a g of x, because it technically is another function, right, because we're plugging in a hole. Right, so we would still have x squared plus 3x divided by x plus 3 if x is not negative 3, and then negative 3 if x is negative 3. Because that's the value of what we get for y, because that's where a hole is. We have a hole at negative 3, negative 3. Right? So a nice little rational function there with a hole in it. How about this one? What value would remove the discontinuity of the given function? Let's see which one you picked. The correct answer was f of 0 equals 1/2. So f was the correct answer. Let's take a look at why we have a removable discontinuity at 0, and the value that plugs in our hole is 1/2. All right, so for this one, it's not like you can factor and reduce. Take the limit to find the y value of the hole. Right? So we're going to take the limit, and that limit is going to tell us where our hole is, right? And at hole, so let's put this in. The limit as x approaches a, f of x, will equal the f of a, right, if our function was continuous. But it also tells us the y value for the hole. Right? So when it's not continuous and it has a removable discontinuity. So when there is a removable discontinuity. Just keep on writing this way. All right, so all we have to do, therefore, is take the limit as x approaches. Of course, where's the problem going to occur? Of course, we know it's 0, right? You can't plug in 0 if you plug in 0 for 2x, you've got 0. If you plug in sine of 0 is 0. So 0 is the problem, right? So we know where the problem occurs. It's at 0. Anything else it's defined for. All right, so we have sine x divided by 2x. They don't match. Right? We need it to be an x, right? So we're going to multiply by everything, by numerator and denominator, by 1/2. So we have the limit as x approaches 0, so we're going this way, of 1/2 sine x divided by 1/2 times 2x. Right? So that's going to give us the limit as x approaches 0. We've got 1/2, and then we've got times sine x divided by x, and so that's just going to be 1/2 times 1, which is 1/2. Right? So that's where the hole is. Right? And so if we wanted to rewrite this as a piecewise function, all right, we would have g of x is equal to sine just 1x, sine x over 2x, x not equal to 0, and then, oops, I need to, here we go, 1/2. Oh, that's my best looking bracket. If x is equal to 0. All right, and so here we have the piecewise function to fill the removable discontinuity. Did you get tricked on that one? I think that one was the trickiest one off the bat. You may not realize, hey, take a limit. Or maybe you think this one was the trickiest one. Right, so f of x equals x minus 2 divided by absolute value of x minus 2. And what did you say was the answer? Well, there were two answers. Right, so both both G and J were correct here. F of 2 is 1. We have a whole, that one's the removable. F of negative 2, we have a non-removable discontinuity there. Let's take a look at figuring this one out. And I have it basically done on the next page. All right, so, and this is another rewriting the absolute value function as a piecewise function. All right, so where we have our issue, right, is in the denominator. Right, so we have the absolute value of x minus 2. Of course, our positive is just x and our negative is negative x, right? The negative 2 is not under the absolute value bars. Right, so our positive piece is x minus 2. The negative piece is negative x minus 2. We've now rewritten it. All right, so now if we take a look at our new function there, right, so we're going to replace the denominator, right, with the correct piecewise part, right? So we've got the positive side and the negative side. So we have x minus 2 divided by x minus 2 if x is greater than or equal to 0, right? You just set x equal to 0. For x not equal to 2, right? Because we see there the x minus 2 and the x minus 2 would cancel, and that would just be 1. That's a horizontal line, right? So 1 if x is equal to 2. It's just like that absolute value of x over x, right? On the positive side, it's going to be 1 because we've got x minus 2 over x minus 2. But the negative side's a different story, right? So we have x minus 2 divided by negative x minus 2, right? So here, the terms won't cancel, right? So in the numerator, because the terms cancel, the discontinuity is removable, right? So that's why this one's removable. You can't cancel an x minus 2 and a negative x minus 2. If you factor out the negative 1, then you've got negative 1 times x plus 2, right? So you can't cancel. The discontinuity is infinite, right? So we have a removable discontinuity at 2, 1, right? That was the removable one. And then at negative 2, you can't do anything about that one. Stuck with that one. Right? So that's the answer on that one. I think that's the last one. Oh, here's the graph of that one, so I'm glad I clicked the page. All right, so here's what this graph looks like, well drawn on a beautiful coordinate plane, hand drawn and everything. All right, so we have that vertical asymptote at negative 2 there. Right? And so for everything less than 0, we're graphing x minus 2 divided by negative x minus 2. We have a piecewise function there. I plugged in a few points so that I could actually graph the thing, and that's what that looks like. We do have a horizontal asymptote, and we have one that's to the right and one that's to the left. Looks like we have a slightly different one, or I probably didn't go up high enough. So the horizontal asymptote should be at negative 1. Yeah, so it's at negative 1. So it just looks like maybe my piece here is going up a little higher than it probably should have because I didn't graph in that asymptote. And then, of course, the asymptote just ends at 0 because we switch functions, right? So we switch to f of x equals x minus 2 divided by x minus 2. That is just a horizontal line. X equals 1, or y equals 1 with a hole in it, and 1, 2 fills the hole. So that's what that one looks like. And I do believe that's the end of this podcast. So we're going to look at making functions continuous in the next podcast. Bye for now.